Hello, everyone. Welcome to this seminar on the foundations of quantum mechanics. My name is Marco Armenta. I'm a quantum software developer at the AlgoLab. Let me tell you what's my goal with this seminar. What I would like to understand is what quantum theory tells us about reality, what we can say about the universe by using quantum mechanics. Now, for this reason and many others, this will not be your usual seminar. Not only because of the questions we'll be looking at, but the way we will approach it. What we will do is we will approach the paper. So this is the first paper we'll be reading. We will approach it as if we were reviewers of a journal, and this paper just landed on our desk. So we will go through it line by line. We will be unpacking a lot of things because I found that it happens very often that one sentence keeps you thinking for a lot of time. And that's something I would like to do here with you. I prefer this to be a discussion rather than me presenting. So it will not be like somebody comes and presents a summary of a paper, because I think that way you can lose a lot of things, a lot of the use that these papers have. Now, this looks like an innocent paper. If you look at the number of pages, it's 4 pages. But I think I passed many, many hours on like just one sentence. And if this takes us many, many sessions, like 10 sessions, then so be it. No problem for me. Now, there will be, oh yeah, one thing I will not do is calculations, because I will make horrible mistakes and I don't want to make you suffer. That's not my goal here. However, there will be moments in which a more sophisticated mathematical theory will be required, which is not usual, specifically for physics students. Like, for instance, for this paper, we'll need the basics for measure theory. And in those cases, I will give you like a crash course, a couple of minutes, definitions, results, so that you can get a taste of what that theory is telling us and why we need it. Also, please push back. Like, if you have at any moment you have any comments, questions, complaints, stop me. Okay, so we can like really extract everything we can from this seminar. I still don't have a fixed schedule for this. I'll try to make it at the same time, but I'm working on that. So instead of that, what we'll do for now is we're going to be recording this. It's a hybrid mode, so you can assist online if you want to. And we'll put these videos on YouTube, on the IQ channel. Yeah, on the IQ channel, and I'll be looking at the comments and the questions there. I'll be responding everything if you want to interact through that way. I'll be also taking suggestions on specific work we would like to read together. But for now, my plan is to go over this paper. This paper has a specific question to it. So the title is On the Reality of the Quantum State. And the question is the wave function, the quantum state, a real physical thing? Or is it just a representation of our knowledge of the physical reality, whatever that means? After that, I would like to go to study Bell's theorems and some experimental realizations of it, because we cannot do foundations of quantum mechanics without doing that first. And also, I would like to touch on some of the work of David Poulain. David Poulain was a professor here at the Institut Quantique. He has a PhD thesis on foundational questions of quantum mechanics. And I'll read to you the first line of his thesis is, why is the world we perceive in our everyday life classical, while the underlying laws of nature are quantum mechanical? Now, I won't read much more, because you will find out if you go read this thesis that the more you read, the harder it is for you to stop reading. It's very, very interesting. I would like to go and study this type of questions too. Yes. Now, before starting, I would like to thank my colleagues at the AlgoLab, specifically Josh Quentin and Simon Verret, for discussing these topics with me, like in between meetings when we were supposed to be doing something else. And now let me tell you how I started thinking about like building this seminar. Last winter, we just delivered a project from the AlgoLab, and I found myself with my intern, Saar Sodin, who's online, 1 week of her time, and I didn't have anything for her because we delivered the project earlier. And I gave her a couple of things that she could start doing, and she chose this paper. And we passed many, many hours, maybe too many hours, discussing this paper, and it was extremely fun. So I hope we can do that here too. Now, without further ado, are there any comments or questions? Oh yeah, final thing. Since we'll be recording this and putting it online, if you have any questions, please ask me, raise your hand or anything, so that we can do it on the microphone, so that the voice gets recorded. If you don't want your voice to get recorded, then just speak out loud your question and I'll repeat it. All right, now, this paper, the authors, this is from 2012. It's very known in the foundations of quantum mechanics. The authors are Pusey, Barrett, and Rudolph. Now, let me start. So, at the heart of much debate concerning quantum theory lies the quantum state. Does the wave function correspond directly to some kind of physical wave? If so, it is an odd kind of wave, as it is defined on an abstract configuration space, rather than the three-dimensional space in which we live. Nonetheless, quantum interference, as exhibited in the famous two-slit experiment, seems most readily understood by the idea that it is a real wave that is interfering. Many physicists and chemists concerned with pragmatic applications of quantum theory successfully treat the quantum state in this way. Let me make a small drawing now, because I've seen people doing this, like confounding if the quantum state is real or not, unlike here at the Institut Quantique. For example, let's say we have a game and I choose a square. And the game is that every two neighboring vertices should have opposite spins. Now, this is pretty simple. So up, down, up, and down. And I solve the problem. But what if it's a triangle? Then I start here up. The next one is a neighbor, so this needs to be down. But this one, what do I do there? The physicist's answer is, I do this, and I solve the problem. And yeah, you solve this problem if this is a real thing in the universe, right? Okay, now I'll continue reading the paper. You won't be looking at it, sorry. But please stop me if you find something interesting. Many others have suggested that the quantum state is something less than real. In particular, it is often argued that the quantum state does not correspond directly to reality, but represents an experimenter's knowledge or information about some aspect of reality. This view is motivated by, amongst other things, the collapse of the quantum state on measurement. If the quantum state is a real physical state, then collapse is a mysterious physical process whose precise time of occurrence is not well defined. Now, this reminds me, that's another thing that I would like to touch on, the Wigner's friends experiment, in which, let me just rephrase it. So you have a room and it's isolated from the rest of the universe, and you have a quantum computer, and you have a person, and you have a qubit here in superposition. And then you have Wigner. Now, this person measures the qubit inside this box, but when is the qubit collapsing? When? Because this is like isolated. So is this, should we treat all of this as the quantum system or only this? Because for the person outside, there's no knowledge about what the measurement is here. Okay. Now, okay, so that's one question that arrives when you start talking about the collapse, the measurement of the wave function. Another thing is things like on an interferometer, if you have, let's say, your laser here, you have your beam splitter, you have your mirrors, and then you have another beam splitter, and you have your detectors. Now, we know that if you do this, then you will have 100% of hits in just one place. But if we put a barrier there, we block this beam, then we will have 50-50, right? But let's look at what happens with only one of the photons. Let's say I throw one photon, and it hits what it's not supposed to hit, here. Then its path should have been like this, that, and this. So when this collapses here, it apparently has information about this path, right? Because this part is blocked, and this is what allows the photons to hit in the other place. So that's another kind of things that are mysterious about the collapse. Like, is it going back in time and taking the other path at the same time? Is it taking, if it's taking the path on the other direction, then so is the superposition real? Is the wave function like actually sensing this part? Anyway, so that's if the quantum state is a real physical state. From the state of knowledge view, the argument goes, collapse need be no more mysterious than the instantaneous Bayesian updating of a probability distribution on obtaining new information. And that's exactly what the postulates of quantum mechanics are telling us. If you start with a state psi, and you measure an observable O, and it gives you some output, it will give you an eigenvalue of this lambda, and the collapse postulate says, okay, now from this moment on, you should treat your system as being on this state. That's just math. Okay, it's not telling me anything about what happened during the measurement. The importance of these questions was eloquently stated by Jaynes, now quoting Jaynes. But our present quantum mechanical formalism is not purely epistemological. Okay, now, epistemological means it means that the quantum state gives us only information. It only represents knowledge. Okay, formalism is not purely epistemological. It is a peculiar mixture describing in part realities of nature, in part incomplete human information about nature, all scrambled up by Heisenberg and Bohr into an omelette that nobody has seen how to unscramble. Yet, we think that the unscrambling is a prerequisite for any further advance in basic physical theory. For, if we cannot separate the subjective and objective aspects of the formalism, we cannot know what we are talking about. It is just that simple. And yeah, I agree that sometimes when we speak about quantum mechanics, experiments, algorithms, whatever, we do use both approach. Sometimes we use it as if the wave function actually exists, is something physical, sometimes as if it's just information and it's just giving us way of computing probabilities. This article presents a no-go theorem. Now, this is the main contribution. If the quantum state merely represents information about the real physical state of a system, then experimental predictions are obtained that contradict those of quantum theory. Now, they will make some more assumptions on this. It's not only just as it is said here. So the first assumption we will make is quantum theory. So let's say 1. And quantum theory for me means the postulates as a textbook approach and all the mathematical consequences of the postulates. And just notice that the postulates do not include like particles or experiments. They just include mathematical things. Now, the argument depends on few assumptions. One is that a system has a real physical state, not necessarily completely described by quantum theory, but objective and independent of the observer. Okay. There exists a real physical state. Now, let me read that again. One is that a system has a real physical state, not necessarily completely described by quantum theory, but objective and independent of the observer. Yes. Can you speak on the microphone, please?
So what is an observer?
Yes. Good question. I don't know.
Okay.
Yeah. Look, let's say you build a quantum system, and I'll work with the most simple quantum system that there is, which is a qubit. So I start with this, then I apply a Hadamard gate. Then we all know what happens, hopefully. We have this state. Now what do we do in quantum mechanics? We do a measurement. What is a measurement according to quantum theory? Is an observable. It's a mathematical object that has some eigenvalues, and that's the thing that we're going to measure. Which observable do I measure? You need to make a choice, right? So I'll choose C now. And this tells me a lot of things about what is the possible outcome. So, and who's choosing this? Am I choosing it? Are you choosing it? And Bell's experiment, they do this cosmic Bell's experiment in which you choose the observables depending on particles coming from quasars on different points that have the light cones that do not intersect, so that they can make this like as independent as possible. But what about this? Is this, am I assuming free will? Right? Yeah, but thanks for the question. That's the question. Yes, microphone.
Following this, I have a proposition for a definition of an observer.
Please do.
It's an agent, or okay, if you want another word, that's an agent.
Could it be an AI agent?
An AI agent.
Okay.
An agent that has access to only one value of a given observable at a time.
One value of
one
a given
eigenvalue.
observable. Okay.
You cannot measure on your measurement apparatus. You cannot have two eigenvalues of the same observable at the same time.
Uh-huh. Okay, because if I choose X here, I have two possible eigenvalues, but one of them will never come out. Right? Okay.
Time. At a given time,
yes,
you choose an observable, and it's a projective measurement. So you will see only one of the two eigenvalues. That's only point.
Okay, but that depends on choosing where you measure, because I could measure here or I can measure there.
You choose an observable O.
Yes.
It has a spectrum of eigenvalues.
Yes.
And at a given time, you say, I measure now O. You will see only one of these eigenvalues.
Yeah, but isn't that one of the postulates?
Yeah, but in fact, it's a postulate about what an observer is.
Maybe I don't get it. Can you re-explain? Like the observer is someone that chooses. Something that chooses.
That chooses and has access only to a single eigenvalue.
Why? I don't see it, because
when you measure, you can see.
Okay.
You can
so when you
on
measure,
your measurement
you can look.
apparatus, you can get 2 or 3 eigenvalues of these observable.
Okay, so
at
the
the same
observer
time.
is able to like interpret or be aware of the outcome.
Yeah, but
Okay.
the outcome is always like a single outcome.
Yes, not probabilities.
Yeah.
Okay, cool. I like that. Another question, comment, complaint, whatever.
So I didn't quite get why you said that we need to make a choice. Why couldn't we have like as an experiment, like an experiment that has been going since like the start of time and it's been repeating and nobody chose it? Why do we need someone to choose an observable? Why can't it just like be there happening?
I think because you need to care about the universe in the sense that, can you give me an example of that experiment?
I don't know, like any physical phenomenon that has been happening for centuries. In practice, it has been like collapsing, right? And nobody has been there to observe it, right?
What? You.
Who set up the measurement apparatus in the first place?
I have an answer, God. But now I need to assume God exists, right? So, yeah.
Like my question is, why are we assuming that we're always doing an experiment? Why can't this just like happen out there in nature? Why does it need to be like a control setup where we choose an observable and then we measure the results? Like,
Yeah, you mean like a thought experiment?
yeah.
Yes, that's a good idea. That could happen. Isn't that because that looks like this Bell cosmic Bell experiment, where you try to set up the experiment or what you measure like according to some physical thing. Yeah, I agree. I agree that I don't know. Yeah. Does that answer the question? No. Okay, all good. Well, not all good, but at least you agree to continue. All right, now, what is this thing? What is the real physical state? I have many questions about now, and it needs to be objective and independent. Now, I'm not saying this physical state is objective and independent. This is an assumption of the paper. So we need to swallow this for now. Okay, there is a real physical state, objective and independent of the observer. So that means that maybe the quantum system already includes the choice of the measurement. Of the observable, sorry. Okay. Now, next phrase, next sentence. This assumption only needs to hold for systems that are isolated and not entangled with other systems. Okay. Nonetheless, this assumption, or some part of it, will be denied by instrumentalist approaches to quantum theory, wherein the quantum state is merely a calculational tool for making predictions concerning macroscopic measurement outcomes. I guess we can all agree with this, right? I will also disagree with this, I guess. The other main assumption is that systems that are prepared independently have independent physical states. Systems that are prepared independently have independent physical states. Now that's okay. Let's say I put two persons producing two experiments. What do I need to ask them, to ask of these people or the setting of the experiment for this to be true? So I will need that these two persons can make independent decisions. Is that free will? Sounds like it, right? But I can also ask quasars with different, with non-intersected, not intersecting light cones. All right. That's the second assumption. There will be a third that is not mentioned that I will make explicit. Yes.
So regarding the quasars with non-intersecting light cones, are we sure that that's actually sufficient to truly make them independent? Because yes, if
No.
we look at, because yes, if they're already far apart, in some sense, their light cones may not overlap, but that's assuming they're always at that distance. If we,
What about
they
the
were,
Big Bang, right?
yeah, if there was a correlation that already occurred at the Big Bang, that could have continued on throughout, and then they're not truly independent.
Yeah, I agree. I agree with that. And we can come back to that when we look at David Poulin's thesis. He has a paper on that called Entanglement as a Witness. So I think that can come back to this. But yeah, okay, if at the Big Bang or like a few microseconds after the Big Bang, you could create like correlations, like these independent quasars with different light cones could in principle be correlated, right? So what are we left with to produce this thing? Free will and what? I don't know. No complaints? Okay, good. Now, to make some of these notions more precise, let us begin by considering the classical mechanics of a point particle moving in one dimension. That's something we can do. Okay. At a given moment of time, the physical state of the particle is completely specified by its position and momentum in phase space. Okay, now that's something we can do. Let's say we have our phase space, one-dimensional. So our phase space is, one-dimensional particle moving in one dimension. So we have only two axes on our phase space, and this will be P. And our particle is completely determined by a point xp. Then other physical properties are either fixed, such as mass or charge, or are functions of the state, such as energy. Viewing the fixed properties as constant functions, let us define physical property to mean some function of the physical state. Okay, let's unpack that. This space, I'm going to call it P because of phase. And they're saying that, okay, physical function, definition, a physical property is a function on phase space. For example, let's say this particle has mass, which is fixed. This is a function from P to the positive real numbers. And what it does is it takes any point here to the mass of the particle. Let's call it M. And it is fixed for this particle. This is a constant function. It's sending everything here to one point. Now, what is a function? Can you give me an example of something that is not a function? Now, intuitively, in one dimension to one dimension, a function is something that we can write here, such that every time I draw a vertical line, I touch the curve in exactly one place. Now, what that means is that, like abstractly, if I have my domain and my codomain, the function is an association rule, the F. And it's sending points here to things here. Let's say it sends F of the dot is the plus, and f of the x is the plus 2. This is a function because I'm associating to each point here one unique point there. But I could have also set f of the dot is plus, but also f of the dot will be the triangle. This is a multi-valued function. What they're saying is a physical property is not one of these things. It's one of these things. For example, the energy. So H goes from P to the real numbers. And what you do is you take the point and you produce the energy. Now, this is not a constant function. This will vary depending on where you are. There are places in which you have the same energy. All right. So a physical property needs to be a function from P. And notice that it doesn't define where should the function go to. Okay, so here is going to positive numbers, positive real numbers. Here is going to real numbers. And we'll do something like that on the space of these physical states at some point. Just a heads up. Next, sometimes the exact physical state of the particle might be uncertain, but there is nonetheless a well-defined probability distribution. And now, here comes my first question. Okay, so they say mu xp, this is the probability. Probability. But this can be either one of two things. Let me see if I have my diagram here. Yes, okay. Now, is this probability saying, okay, I don't know exactly what it is in phase space. So it could be like I have like a Gaussian precision. So I could say, okay, I have like level curves like this. And if you look from this side, then you see a Gaussian. And you go from any side here, you will see a Gaussian, right? Something like this. And the point particle is here, but I don't know. Is it this, or is it I have my particle here, and there are places that have the same energy, and we all know how these look like this. Now, is this that, or is this a probability distribution in here? Let's say a uniform distribution on like the support of this all the states that have the same energy. I'm asking you. No? But does it make sense that I'm confused here? Yeah? Yes.
It really could be either, I would say. It's just in the latter case, you're essentially assuming the microcanonical ensemble, and that's one way you could think of it. We just assume that essentially over time that the distribution, if you were, let's say it would be over time, you measured over time, you assume that distribution would be the equal energy curve. But that's one possible distribution. I would argue it could just be anything over phase space, because it really is in this case just describing our lack of knowledge of what the actual state is.
Yeah.
So it could be either of the case.
Okay. But this assumes that I know the energy like precisely, right?
Okay, yeah. If you're taking a probability distribution that, microcanonical ensemble, yes, it's a specifically defined energy, and then the distribution will be equal over any possible state at that energy.
Yeah, because if I also have precision on the energy, then this thing will be something like that, right?
Yeah, something like that, yeah.
Okay. Any other question? No? Okay. Cool. Now, let me just reread that sentence. But there is nonetheless a well-defined probability distribution. So that tells me nothing, right? Okay. Although mu xp evolves in a precise manner according to Liouville's equation, it does not directly represent reality. Okay. Yes, okay. So it's not that the probability density here exists, it's real. It represents my knowledge about it. So it's like this like epistemic view of the wave function. Like they're trying to make an analogy with it. Rather, mu xp is a state of knowledge. It represents an experimenter's uncertainty about the physical state of the particle. Yes, same thing. Now consider a quantum system. The hypothesis is that the quantum state is a state of knowledge. Okay, next hypothesis. Or psi is a state of knowledge. Where am I? The hypothesis is that the quantum state is a state of knowledge.
Sorry.
Yes,
State of knowledge to who? Again, is this the observer or is this
the observer. Yes,
the same observer?
you and me. Yes, I think so. Hence, assume some theory or model, perhaps undiscovered, that associates a physical state lambda with the system. Aha, undiscovered. How much time do I have? Okay, plenty. Okay. So let's say I'm going to start with my running example. Physical system. Yeah, they say physical system. Hence, assume some theory or model, perhaps undiscovered, that associates a physical state lambda with the system. What is the system? Is the system I have? Okay, I have many proposals for the system. Is this the system? Or with the choice of the observable, the system? Or is this the system? Who votes for the first one? One vote, two, because that's what I think. Who votes for the second one? Is this the physical system? No. One vote. Who thinks this is the physical system? Two votes. I'll actually put 2 plus n. I'll assume everyone else votes for this.
Marco,
Yes.
I would argue it's none of those because
Okay.
okay, to me, in some sense, the closest to the first one, but this is describing how to prepare the physical state. It's not that this circuit is the physical state.
No, I'm not talking about the physical state. I'm talking about the system. What is the system?
Okay, then what do you mean by system versus physical state?
I don't know. Look, yeah, that's gonna be my favorite sentence. I don't know. Hence, assume some theory or model, perhaps undiscovered, that associates a physical state with the system. So that means that I need to choose between these three to associate to each one of those a physical state.
I would still say it's not a. I don't know if I would still even consider that a particular system. It's associate to the system a particular physical state. Okay, I guess it's going to be a collection of physical objects, and then at some point in time, what is its state, and then it's assigning that.
With the choice of the observable after the measurement, before the measurement. You see why I'm confused? You
Yeah.
agree that I should be confused?
I'd argue it'd be okay. Okay, we would tend to say we can argue that before versus after measurement, whatever system it is, it has a different state. or could have a different state,
A different physical state.
different
Before
physical
or
state
after measurement.
before or after measurement. It
Okay.
could. But then that tells me then that the measurement is not part of the system because we're describing the system as having its own state before or after the measurement. The measurement was just a process that modified where the system is sitting, but it's not the system itself or part of it.
Modifies the system. So you're assuming that the system will be like this superposition? So are you assuming that the quantum state is part of the system?
Okay, I would say the quantum state is an attempt to describe the physical state, but I guess in this first circuit, I would say the physical system would be the qubit.
Yes.
It's probably the closest, I would say. And then the circuit is just some protocol of what is applied to the system.
Okay, so let's say the system would be a physical qubit on a chip.
Yeah, I'll
right?
say
Those
isolated.
measurement on C is fixed. I just need to decide if I measure it or not and when I measure it.
Yeah, but that's
Okay.
all outside of the system.
Okay,
That's
Okay.
what I would argue for.
cool. I kind of agree. And then we'll see that I think they will disagree with you in the paper, but wait for it. More complaints? No? Okay. If a measurement is made, so that means that it is not this. It is either one of these two. If a measurement is made, the probabilities for different outcomes are determined by lambda. Okay, now this physical state is lambda. If a measurement is made, the probabilities are fixed by lambda. That looks like the quantum state. It sounds like the quantum state. It smells like the quantum state. Okay, so if a measurement is made, the probability outcomes are determined by lambda. Okay, but now let me come back to this. So there exists a real physical state objective and independent of the observer. So is it that this system or this experiment is preparing for us this psi from quantum theory that we know and love? But actually what it's doing is preparing lambda. We don't know what lambda is. We don't know the theory that describes lambda and how lambda behaves. But it could be that what this is actually doing is this. But we don't have access to this. We only have this like representation of our knowledge to lambda. And when I measure, let's say I measure C, I'm invoking my free will, and then I measure 0. Was it that lambda was 0 all along? Or is lambda implying that the probabilities for 0 are 1/2 and the probabilities for 1 are 1/2, just like the quantum state? So I have like these two views for lambda. This thing, I'm preparing the same experiment every time, and I'm getting different results. Does it mean that I'm preparing, like sometimes I prepare lambda prime, but I don't know because I don't have access to I don't have complete information about what's happening with the physical state. And sometimes this lambda prime is 1. Or am I always preparing lambda with this, but I don't have lambda and lambda helps me compute probabilities? Or this hidden theory helps me prepare compute probabilities? Or is it like this? Do you see that that could be like either one of these two? And now here it says objective, right? So that means, because the lambda, the superposition, is it objective or is it subjective to our knowledge of quantum theory? It's independent of the observer, the lambda too. So who's reading the result of this if it's independent of the observer? What's happening here? So it could be either this or that. Now, in principle, it looks like the second one, because look, if a measurement is made, the probabilities for different outcomes are determined by lambda. Okay, it looks like the second one, but I'll come back to this later. If a quantum system is prepared in a particular way, then quantum theory associates a quantum state, psi, but the physical state lambda need not be fixed uniquely by the preparation. The physical state lambda may not be fixed uniquely by the preparation. So that means that with this preparation, I could be preparing this or that. I could be preparing different things. Or I can be preparing, let's say, lambda prime, that is going to give me now other probabilities. Probability of 0, probability of 1. Right? But maybe like these physical states are different. Like in quantum theory, like if we put states with a global phase different, they are different quantum states, but they compute the same probabilities. All right? Or it could be this. Okay. Now let me reread that. If a quantum system is prepared in a particular way, then quantum theory associates a quantum state psi. But the physical state lambda need not be fixed uniquely by the preparation. Rather, the preparation results in a physical state lambda according to some probability distribution. Now, and this probability distribution, I'm running out of space. This is what they denote by mu, psi of lambda. This is the probability that preparation psi, but what if psi for us? For us is an initial state and then unitary evolution produces the physical state lambda. So that means now I have, like, if I prefer this part here, now I have a probability that lambda is produced and a probability that lambda prime is produced, or other lambda double prime, things like that. And each one of those produces probabilities or allows me to compute probabilities. Or I have that this same experiment, this same preparation, produces this with a specific probability and produces that with a specific probability. And those probabilities will be, so in this case, mu psi of lambda will be 1/2, and mu psi of lambda prime will be 1/2. Right? Either one of those two should work, yes.
Actually, kind of wondering if either you could say either there's a false dichotomy or if you're maybe inserting a bit more than what they're trying to say, in the sense that they're just saying that, okay, it prepares some lambda, could be, yeah, some lambda such that when you measure, you get these probabilities. ultimately.
No, they say the lambda predicts probabilities. That's what they say. Look.
Yes.
If a measurement is made, the probabilities for different outcomes are determined by lambda.
Yes.
Okay? Lambda is not the outcome, not necessarily the outcome of the experiment.
What? Like I think that's kind of what I'm getting at here. In that, on the right, you have that the outcomes are the measurements, but on the left circle, you're saying the
It's like
outcomes is specific
deterministic.
lambda.
Right? Yeah.
So that's where I'm like, I think if you were to take the first circle here, you're inserting saying that you're for sure preparing a specific lambda. Well, really what they're saying is, or the wave function basically is ultimately what you're preparing is a lambda or some lambda that gives you these probabilities.
Yes. Yeah, I agree.
Yeah. So then
Yes.
it could not be this.
It could not be this one.
Yeah.
Okay. Okay. I agree.
Okay.
Yeah. It will be something like this instead.
Yeah.
Okay. Everyone agrees? Okay. Okay. According to some probability distribution. Now, what do I have here? Yeah, that's exactly that. Okay, should be fine. Now, given such a model, Harrigan and Speckens, now they make a reference to another paper, give a precise meaning to the idea that a quantum state corresponds directly to reality or represents only information. To explain this, the example of the classical particle is again useful. Here, if an experimenter knows only that the system has energy E and is otherwise completely uncertain, the experimenter's knowledge corresponds to a distribution uniform over all points in phase space with the same energy, which is the thing that I just erased there. So if we are on phase space and we have a point here and we take all of the things that have the same energy, so this will be, so according to this one, I will have probability distribution XP. E is a fixed energy, so E, this is fixed. And now this mu exp is a uniform distribution on all the points in phase space that have the same energy. So it'll be a uniform distribution here, assuming I can measure energy to an infinite precision. As the energy is a physical property of the system, different values of the energy correspond to disjoint regions of phase space. Yeah, so if I take another E prime, which is not E, then that will give me another set inside the phase space that has this energy, and these two do not intersect. Right? And now this these shapes, each one is the support of each one of the functions. And the support is, so let's say the support of this mu E xp is by definition all the points in phase space. I'm going to call P x prime such that the energy is not zero. No, wait. The energy is equal to E. So this is a subset of phase space. This lives inside phase space. On the other hand, if two probability distributions have overlapping supports, so that means that at some point, now here he's not talking about energy. He's talking about any other function on phase space. So because for energy, this doesn't happen because energy is a physical property, so it is a function. But what could happen is that you have now another function that is associating now this. So now I have points that intersect all of these things. There is some region of phase space where both distributions are non-zero. Then the labels cannot refer to a physical property of the system. How much time do I have? 5 minutes. And they do it like this. They say, okay, this is my lambda axis. And this is my probability axis. And I have one thing here that represents the probability distribution for mu L. Now, mu L is a function of physical states. So I evaluate it on lambdas. And if they have, so for this to be a physical property, you will need now to evaluate it on something that has a disjoint thing here. Because if you don't, if you do it like this, then the things here, they could be assigned these values, for instance, that corresponds to the both different probability distributions, L prime. Now, this wouldn't be a function. This wouldn't be a physical property of the system, because I will be assigning like two different things to the same point. Now, this intuition is bad, because I'm assuming that lambda is one-dimensional, that I can plot it like this, I can visualize it. And I'm also assuming that the thing that holds the lambdas is a set. Now, for those of you who know set theory, that means that I have something that is small enough. So a set is a bag of things. I can put things in it. But what if it's what we call a class? Now, the problem with a set is, let's assume I would like to construct the set of all sets. Is that set inside itself? No, that's a problem, right? So we're assuming this doesn't happen here. So we're assuming that whatever holds the lambdas is a set. It could be the other thing. And now maybe I can use category theory to describe what the lambdas are, but now I cannot plot these things. And I need to deal with more abstract theories. But for now, we have the fifth assumption that whatever it is, lambda, that holds all physical states is a set. Now, I think I'll stop there. And these are our 5 running assumptions so far. We will add one more to this later.